Okay, hello everyone. This is the video part 2 of my thesis dissertation to obtain the PhD in electrical engineering from the University of Memphis. And by the way, I'm Raul Castaneda, just in case that you didn't see the part 1 of this video. So, okay, it's time to talk about the research number 4. The research number 4 was PyDHM, a Python library for applications in digital holography and digital holography microscopy. So the motivation of this work is because of the lack of a universal open source tool for the globalization of digital holography microscopy. So, of course, there are some open source and available tools like libraries and plugins to develop different tasks in digital holography and digital holography microscopy. However, we notice that they are not an implementation for different architecture in DH and DHM. So for the reason we say like, okay, why not to develop a Python library to work in DHM in different architectures. When I say different architecture, I mean application in line of axis, as slightly off axis, propagation of optical fields. Okay, so and for this reason, we propose the creation of PyDHM, a Python library for developing different tasks focusing DH and DHM. So the Python library PyDHM is composed by four packages: utility, phase shifting, full compensated, and numerical propagation package. So this is like the general structure of the library. I'm going to explain each package right now. So the first package is the utility package. So the utility package, you can find different functions that are necessary when you are working in DH and DHM. And also they are function to image processing in general. For instance, you can find function like image read, image show, compute intensity, amplitude, and phase, of course, for the digital holography. Functions to compute the Fourier transform, the inverse Fourier transform, and circular filter, rectangular filter, and a specific algorithm to reduce the speckle noise, that is the hybrid Mayer 2 filter. I will present this algorithm at the end of this presentation. So package number 2 is the phase shifting package. This package contains the phase shifting strategies for reconstructing the complex amplitude distribution in line and slightly off axis system. You can find 6 different methods. Some of these methods are the conventional implementation, for instance, 5, 4, and 3 frames for inline holography. And also you can find blind strategies, the blind strategies that was developed by the Optical Imaging Research Lab. This is a sample an example of how to implement the phase shifting package. So the first task, of course, is import the library, import the package, import the utility package, in this case, the phase shifting package. Read the holograms. In this case, I am reading 5 holograms. And of course, finally, call the specific function that you want to implement. For instance, phase shifting 5 holograms, or phase shifting 4 holograms, or phase shifting 3 holograms. These are the parameters that each implementation needed, and compute the phase. So this is the holograms, and this is the reconstruction for PH5, PH4, and PH3. Okay, the package number 3 is the fully compensated package. This package contains algorithms for obtaining the phase reconstruction of digital holography microscopy. without or with minimal perturbation in of axis system. So this package contains four different strategies: full row research, efficient row research, cost function search, and compensation not telling. This is an example how to implement this package, the compensation package. It is too similar to example that I showed you before. Import the libraries, of course, read the holograms, and call the specific function that you want to implement. When you call each function, you need to input the parameters. So for instance, in the compensation with the const function, the parameters are the hologram, the wavelength, and the pixel size. So these parameters depends, of course, of the compensation method that you are using. And this is the Fourier transform of one of these holograms and the phase reconstruction from the same sample, globus melanogaster fly. This is using the FRS implementation, and this image is using the ERS implementation, and this is using the construction implementation. Okay, finally, the package number 4. Package number 4 is the numerical propagation package. This package contains algorithms that allow the numerical propagation on the scalar complex diffractive wave fields at different propagation distance. So in this case, you can find the angular spectrum, the Fresnel transform, and the Fresnel-Bluestein. So this is an example to reconstruct images of axis for a hologram recording of axis architecture, where it's necessary to create a propagation in order to focus the information of the hologram. So this is the hologram, this is the Fourier transform, this is the Fourier transform after create a spatial filter, in this case a circular spatial filter. And these are the intensity reconstruction with different propagation distance. So, of course, again, the first is import the package, import the utility package, import the numerical propagation package, read the hologram. In this case, I show in this example how to compute the Fourier transform, how to create the spatial filter, and here the propagation using the angular spectrum. So here we have the reconstruction to different propagation distance. So you can realize how the information start to look focus. You compare this image with this image here. Okay, this is a brief summary of the PyDHM library. So we have introduced PyDHM, an open source library to reconstruct holograms recorded by a broad range on optical DHM configuration. The library is in a GitHub repository. Whatever person can use the code and customize. Instruction videos for using the proposed library and PyDHM library is posted in the GitHub group and also in YouTube in this same page, the optical imaging research laboratory. This work has been presented in Imagine Applied Optics Congress, was published in +1. Okay, so it's time to talk about research number 5. So research number 5 is a learning-based model for video array phase images reconstruction in digital holography microscopy in off-axis architecture. So the motivation borns because when you are working with off-axis digital holography microscopy, one of the more important features is that it's a single shot technique. So Single shot technique means that you can retrieve information at real time or at video rates. However, the conventional algorithms don't allow to retrieve face images at video rates free of aberration. So what is the best scenario? The best scenario is that from a hologram, you can retrieve the trustworthy face information, right? The best scenario is that recovery of face mask at video rates. However, as I said before, the conventional algorithm don't allow retrieve the face images without aberration, free of any aberration. So, for instance, this is a video of face reconstruction by red blood cells moving using conventional strategies. Let me reproduce this video. Oh, excuse me. Okay, I need to. Okay, so this is conventional composition method. So they are phased out between different frames. You can observe. And the background is not homogeneous. So at the end of the day, we consider that this is unreliable phase quantification, right? So for this reason, we thought, why not implement deep learning strategies to obtain face images at video rates? So one of the first tasks that was investigated if there are applications of deep learning focusing digital holographic microscopy to retrieve face information, of course. And we found that there are applications, but not focused in reconstruction at video rates from raw holograms. So for this reason, we thought, okay, why not use deep learning strategies? Deep learning are a short description algorithms that endeavor to recognize undirected ratios in a set of data. So we have input layers. After the input layer, we have the hidden layers. In the hidden layer, of course, what happens the magic. Happen the magic because in the hidden layer, different math processes start to um, to happen to happens in order to recognize parameter or the more important feature of the input data. And the last hidden is the output layer. So there are several kinds of deep learning models, but we are interested in a specific deep learning models called the convolutional autoencoders. Convolutional autoencoders are unsupervised learning models that are composed by two parts, the encoder part and the decoder part. The encoder part has the task to keep the more important feature or learn the more important feature of the input data, and the decoder part has the task to retrieve the original information. Autoencoders has been widely applied in dimensional reduction and data noise removal. In fact, one of the first tasks of the convolutional encoder used for image processing was reduce pepper and salt noise. Okay, so this is all the model that we propose, a convolutional encoder, and um, that that has the encoder and the decoder part. So the original idea was from a hologram, we want to train a model that learn to obtain the face images, the face image information, of course, from the hologram. So the our encoder that we propose is composed by the encoder part that has three um, stage. In each stage, different convolutional processes start to happen in order to learn the important feature of the hologram. And of course, the decoder part is a mirror version of the encoder when the convolution starts to happen in order to retrieve the phase images information, the phase image information. So to validate the performance of the proposed method, we need to train the model, right? So one of the challenges that you have when you are working with your learning models is the data set. So at the beginning, we didn't have the data. So we thought, okay, we need to create a data set. And for the reason, we simulate 6 different types of cells. And the simulated cells, we random distribution and density in background of 256 by 256 pixels. So for the reason, in some cases we have 3 cells, in other cases we have 6 cells or 8 cells, right? We simulate off-axis hologram, and the interference angle in the holograms are diverse in order to increase the method's applicability and mimic as real as possible in real scenario. So in this Fourier transform, in the direction of this fringe, you can realize that there are different inclination between the interference of the object beam, and a total of 4,300 holograms and respectively Hamilton phase reconstruction images we obtain to the simulate data set. Okay, so after training the model with this simulate data, we obtain these outcomes. These are the outcomes for amplitude, and these are the outcomes for the phase, and this is the reference method and the outcome with the convolutional model. So we notice that the mean square error between the images obtained for the reference method and the convolutional method is almost zero. So almost zero means that our model has the capability to retrieve phase and amplitude information almost in the same values that the reference method. So we say, okay, this is a good outcome. Why not provide with real data set? So we train the algorithm use sample unstained red blood cells. For creating the data set, we use a max sender interferometer, and we record holograms and obtain its respective phase images using convolutional method. Total number of images for training this model was 24,000. 80% of this data was used for training, and the remaining 20% was used for the validation. Okay, this is the outcomes. So the holograms, the reconstruction using the reference method, and the reconstruction using the convolutional model. So in this image, we can notice some important features. So let's start by the red cycles. So in the red cycles, you can observe that there are a more homogeneous background with the convolutional model. We thought that this outcome is, we are waiting for this outcome because if you think that convolutional encoder was implemented to reduce noise, so this is an outcome that we are waiting for, right? Other interesting result is that the conventional models, the reference method, some cases, the phase reconstruction has perturbations. However, the reconstruction that we obtain don't present this problem. So we are obtaining homogeneous information from the phase of the red blood cells. Okay, but there are a problem with the convolutional model is for the process of the convolution, some important information of the border of the red blood cell is completely deleted. So the shape of the red blood cell is not well defined. Bearing in mind this problem, we think, okay, we can use other models, other deep learning models. And for the reason we thought that we can use generative adversarial networks, the second models. So second models are composed by two parts, a generator and a discriminator. The generator has the task to create face images using a unit model inside the generator. And the discriminator has the task to say if the image created by the generator is fake or not. Okay, so in this case, we use 1,800 holograms, and again, we split 80% for training and 20% by validation. So second models needs to metrics for the convergence. So the metric that we implement is the trace and summation metric, the metric that I explained before in result number 2, and the standard deviation. Okay, this is the outcome that we obtain, the holograms, the face images using the reference method, and the face images obtained by the second model. So almost these images present the same feature that the outcomes obtained by the convolutional autoencoder. However, you can note that the second model retrieved the trustworthy shape of the red blood cells. So this is an interesting outcome for us. This is like images when we are represent the 3D profile using the reference method and using the second models. To validate the generalization ability of the proposed of the system diversity, the Asian holograms were recorded using a common path, well, using a Fresnel by prism. So this is the phase image reconstruction obtained with the reference method using the unit model and using our second model. And we can observe that our second model present high accuracy, reconstruct the specimen in detail. Well, this is the, oh, excuse me. This is the video that I showed you before using the conventional methods. And this is the outcome that we obtain with the second method. So you can realize that there are no phase jumps between different frames, and the phase information of the red blood cells are homogeneous between the different frames. Okay. So as summary, we have reported two learning-based strategies for fully reconstruct quantitative phase images for human red blood cells using convolutional autoencoders as second models. To the best of our knowledge, this is the first learning-based method to reconstruct of active DHM holograms of biological samples with minimal phase distortion from RAM holograms. RAM holograms means without the need of robust pre or post numerical processing. We think that it could be a straightforward standard to reconstruct quantitative phase image of other kind of biological samples. Okay, this work was presented at IEEE Photonics Conference and has been published in Sensors. Okay, this is the result number 6, by the way, the last one. Uh, the research is about the hybrid medium to filter a new algorithm to reduce speckle noise. So, what is speckle noise? Speckle noise is a problem that affects all imaging techniques that use coherent lines and sort of illumination. Of course, speckle noise affect digital holography and digital holography microscopy. The speckle noise generally looks like a pattern of granular dark and brightness point that affect the quality of the image. There are conventional metric to quantify the speckle noise that the name is the speckle contrast. And the speckle contrast is calculated like the standard deviation divided the mean intensity in a region of interest in a specific region of the image, of course. So the problem with the speckle is that the speckle noise distorts the image, the information in the image, the quality, the dynamic range. Okay. So there are different approach to reduce the speckle noise. Some of them works in the frequency domain, others in the real domain. But in general, all these strategies are focusing the use of filters. So these methods that appear in this slide are the considered state of the art. Okay, so what is the problem with this algorithm to reduce the speckle noise? So the problem is that there are a limitation because sometimes filters present a trade-off between the reduction of the speckle noise and the reduction of the quality of the image. I mean, some cases you can reduce the speckle, but at the same time, you reduce the resolution of the image. So for instance, this is the original image reconstructed amplitude of a dye. And this is the the image after apply the medium filter, right? So if we look inside this yellow rectangle, we can notice that the speckle noise has been reduced, of course. Look the region against this region. However, there are a problem. Let's zoom in the yellow field of view in both images, of course. Clearly, you can notice that the speckle noise has been reduced, but at the same time, the information of the image has been deleted. Look, here you can say that there are 4 points, but these 4 points are completely deleted in the image after applying the media filter. So the application of the media filter reduces the speckle noise as well as the resultant image is more blurred than the input image. So there are a reduction in the resolution limit, right? So okay, for this reason, in this work, we propose a computational method to reduce the speckle noise. The name is the Harry-Mayan 2 filter. And let's explain our method right now. So we can consider that our original image can be represented as a matrix, right? So in the first step, the algorithm applies a median filter with a kernel size 3 by 3 over the original image, of course. So after applying the median filter, the image obtained after applying the median filter is computed with the original image, okay? Is computed in such a way that the method compute the mean, okay, between the original image and the image obtained after applying the median filter with a kernel size to 3 by 3. So later, the algorithm applied a median filter again, but this time with a kernel size 5 by 5 over the original image, but in this time, the mean is computed with the previous outcome. So the algorithm starts like a process of a waterfall process until a kernel size defined by the user. So this is the pseudocode of the hybrid median 2 filter. So the method needs two inputs, the original image and the maximum kernel size. And the algorithm enter in a while loop until that is broken, where the kernel size will be equal to the value defined by the user, right? So for comparison purpose, we have implemented the conventional median filter and the hybrid median 2 filter. And we realize interesting outcomes. So let me explain this plot. So the red line is the line of the hybrid median 2 filter, the speckled contrast. And the blue line is the conventional median filter. So we can realize that after iteration number 4, that represents a kernel size 5 by 5, the reduction in the speckled noise is almost the same. However, there are a huge difference in the resolution of the image when the method are applied. So in order to quantify the resolution over in each image, we compute the full Willard maximum for a step function. In a step function, the derivative of that step function must be a delta. So if the full Willard maximum start to increase, it means that the resolution of the image is poor, right? So the green line is the full Willard maximum for the conventional median filter, and the purple line is the full Willard maximum by the hybrid median 2 filter. And we can realize that always the full Willard maximum for the hybrid median 2 filter is lower than the measure or the full Willard maximum with the conventional median filter. So this represents that, of course, we are losing information of resolution, but in a minor quantity than the conventional median filter using the hybrid median 2 filter, right? So also we had compared the performance of the proposed method with some of the considered state-of-the-art. So we have the conventional median filter, the block matching and 3D filtering, the non-local mean, the winner function, right? The two-window Fourier transform. So we realize that the best outcome of the homogeneous outcomes are presented by the BM3D algorithm and the hybrid median 2 filter. So, for instance, the non-local mean reduced for the case of the horse. We have here in this image, sorry, we have the reconstruction of a die and a horse. In the case of the horse, the reduction of the spectral contrast is 0.28 by the non-local mean. However, you can realize that the information of the sample is completely blurry. However, by the BM3D, the spectral reduction is 0.36, and by our proposed method is 0.38, and the information of the horse is presented in the image after applying those methods. Okay, the relevance of the proposed method to reduce the spectral contrast and mitigate the blurry effect have also demonstrated in quantitative phase images, I mean in digital holographic microscopy. In this case, we use the same approaches to the comparison, but in this case, we use a start target. So first, we define our region that we consider the resolution limit. So this is the original image, and after applying the method, we start to notice that, for instance, the non-local mean reduce the resolution. Other methods like the BM3D in this case affect in a high way the the resolution. However, the hybrid medium filter preserve the same resolution that the original image. Regarding the speckle controls, we are reducing the speckle control 0.86. Other approach that reduce the speckle contrast in in uh in, in a better way. However, the resolution limit is reduced, like in the case of the non-local mean. Finally, we analyze the performance of the hybrid medium 2 filter using a biological sample, in this case, the Drosophila melanogaster, to quantify the reduction of the speckle noise. We count the phase jumps over the original image and the image after apply the methods. And we observe that the reduction with the hybrid method is higher than with the other ones. So this is the original image. This is the image after apply the hybrid method to filter in this specific range. So, okay. As summary, we propose an effective single-shot image processing method to reduce the speckle noise in digital holography and digital holography microscopy. The novelty of the proposed method is the synergy combination to well-known approach in image processing, the median and the mean filter. A highlight mark of the hybrid median method is the capability to provide the noise spectrum in both amplitude and phase imaging, with deteriorating the resolution. Also, we consider that our proposed method is simplicity and efficient. Only a single parameter is needed, and is the maximum kernel size. The work has been presented in Imagine Apply of this Congress, and we published a paper in optical engineering.